The train has been accelerated to a velocity v. Now, things are about to get interesting. In this video, we will explain what the special relativity is about and deduce the formula for time dilation. But first, here's a brief biography of Albert Einstein, the father of the special and general theory of relativity. Albert Einstein was born on March 14, 1879 at Ulm, Württemberg, Germany. In his younger years, he studied at the Luitpold Gymnasium in Munich. In 1889, a Polish medical student, Max Talmud, frequented Einstein's estate and started to teach Einstein about higher mathematics and philosophy. One of the books he was introduced to resulted in Einstein starting to ponder on questions such as what a beam of light would look like if you run along it with the same speed. Because of these kinds of thoughts, he wrote his first scientific paper at 16 years of age, titled The Investigation of the State of Ether in Magnetic Fields. While he was studying James Clerk Maxwell's equations that describes light and other electromagnetic phenomena, Einstein discovered that the speed of light is constant, no matter who is observing it, which conflicted with Isaac Newton's laws of motion. This realization led Einstein to formulate the theory of relativity. In 1905, he published 4 papers in the physics journal Annalen der Physik. The papers were about the photoelectric effect, Brownian motion, special relativity, and equivalence of matter and energy, E equals mc squared. In November 1915, Einstein completed the general theory of relativity, which correctly predicted the perihelion of Mercury's orbit around the Sun, which could not be correctly calculated with Newtonian physics. The general theory of relativity also predicted a deflection of light around the Sun when a planet orbited nearby. This deflection was confirmed by observations made by Sir Arthur Eddington during a solar eclipse in 1919. Albert Einstein received the Nobel Prize for Physics in 1921 for his work on the photoelectric effect, rather than his work on relativity, because this theory was still controversial by that time. Einstein spent the rest of his career attempting to develop a unified field theory for the 4 fundamental forces. On April 17, 1955, Einstein died of an abdominal aortic aneurysm. The special relativity is about the consequences that will happen when the speed of light is constant, no matter what the frame of reference you are in, and no matter the speed of your frame of reference. As a consequence of this weird property of light, distances, time flows and masses change depending on which frame of reference that observes the phenomena. But I'm getting ahead of myself. First, we have to define what a frame of reference is. A frame of reference is basically a coordinate system that can have velocity relative to other frames of references. Objects inside a reference frame can have different positions and velocities relative to their frame of reference. In special relativity, frames of reference also come with a time, since different frames of references can have different rates of time relative to each other. In order to go down the rabbit hole of special relativity, we have to use 2 postulates that Einstein formulated in order for this theory to be valid. A postulate is an assumption about some fact that makes a basis for reasoning. The first postulate is the postulate of the principle of relativity. The postulate reads that the laws of physics take the same form in all inertial frames of reference. This means that the laws of physics are the same in all frames of reference. The second postulate is the postulate of the invariance of C. The postulate states that the speed of light in free space has the same value c in all inertial frames of reference. Now imagine two frames of reference f0 and f1. f1 can move with a velocity v1 relative to f0. One way to see it is that f1 is stationary and f0 is moving backwards. This is how the guy in f1 sees it. Both f0 and f1 have their respective clocks, and they can show different times relative to each other. Not only that, if the guy in f0 looks at f1, he can see that the time in f1 moves more slowly than his own clock. And because f0 is moving away from f1 as well, then the guy in f1 thinks that his clock moves faster than the one in f0. We will soon prove that this is a fact. Both guys in their respective frames of reference are now turning on their torches. We know that both of the guys perceive the light emanating from their torches have the speed c relative to themselves. If we make the guy in f0 an observer of f1, he will measure the speed of the light from its torch to c as well, even though it's moving away from him. We can make the guy in f1 an observer of the torch in f0 as well, and he will notice that even though the torch is moving away behind him with the torch pointed at him, the speed from that torch is not lower than the speed of light as you would expect, but is instead exactly the speed of light. The fact that the speed of light is always the same, no matter how fast you move alongside the light, is a very strange thing to wrap your head around. We are about to see an example of how it works, and hopefully it will make a little more sense to you. Here we have a train car. In the car there is a guy named P and a set of mirrors, one on the floor and one on the ceiling straight above it. In the train car we define a relativistic frame of reference f with its own time t. We then imagine a guy standing in the grass just outside the train car. We call him P prime. P prime also has a reference frame, which we call f prime. This frame of reference has a time of its own that we call t prime. In the middle of the floor mirror, there is a laser, and it has such optics that the laser shoots a pulse of light. It passes the optics, bounces on the top mirror, and returns to the floor mirror, where it bounces back up again. We imagine that the laser light from this setup continues to bounce indefinitely once started. Notice how the photons bounce up and down vertically. There is no horizontal movement of the photons that person P can perceive. The light from the laser travels at the speed of light in free space. Therefore, we ignore the effects of light traveling through a medium, such as air. Another thing to consider here is the scale of things. We can either pretend that the speed of light is very low in comparison to the speed of the train car, or we can pretend that the train goes very fast compared to the true speed of light. We will assume the latter, and because of this, the rate of change in both the clock inside the train car and the one at the ground is insignificant. I could show an exaggerated movement on both clocks, but I think the important takeaway here is how the laser beam behaves for both frames of reference. The train has been accelerated to a velocity v. Now, things are about to get interesting. Even if person P is moving forward with velocity v, he still sees the beam moving up and down. Person P prime, however, sees an entirely different thing. He sees the photons bounce with a horizontal and vertical movement at the same time. That is, he is seeing the beam first bounce diagonally to the right and up, and then bounce right and down diagonally. The distance the photon has traveled from the bottom to the top is now longer for P' than for P. Because the speed of the beam is the same for both, then the change in time must be different for both persons. Putting all this knowledge together, we understand that the only way to make the light hit one of the mirrors for both observers is that if the distance traveled is longer as perceived by one observer, then that observer must also perceive that the time has taken longer from start to end along that distance. Therefore, if something moves fast relative to you, then any light-based process in that thing takes a longer perceived path, and thus the time must take longer as well in order for the speed of light to be constant. The light-based process does not have to exist in the object for the flow of time to change like this, however. We can now use simple geometry to actually prove that our little thought experiment actually holds true. Between the first event and the second event, we can span a right triangle between the starting point in the first event, the starting point of the second event, and the beam position at the ceiling in the second event. The hypotenuse of the right triangle is c times delta t prime, because it is the distance the photons have traveled between the mirrors as perceived by P prime. The short cathetus is c times delta t, because this is the distance the photons have traveled between the mirrors as perceived by P. Finally, we have the long cathetus, which has the length v times delta t prime, because this is the distance that the train car has traveled between the two events. We will write down the relationship between the side lengths of this right triangle in equation form. We will apply Pythagoras' theorem for this. If you are unsure of how to use Pythagoras' theorem, then you can go back to one of my earlier episodes, which explains how it works and how to deduce it. You can click the link provided in the top of this video. Now let's move the terms containing t prime together on the left hand side. We then divide the whole equation with c squared. After simplifying away the c factors on two of the terms, we move the remaining c squared denominator into the numerator. After which we factor out this v over c term. We factor out the delta t prime squared. Then take the square root over the whole equation. Finally, we take the square root over the 1 minus v squared over the c squared factor and move it to the right hand side and simplify. This is the equation for time dilation, meaning the stretching of time. The higher the velocity, then the longer delta t seems to be for the P' observer in relation to his own clock. Note that delta t prime is observed delta t in the reference frame f, and not its own pace of time, which is simply delta t, just like the guy in the train car. Now let's take a look at the extreme cases. What if we set the velocity to 0? Then we can see that delta t prime equals delta t. This makes sense, because then both frames of reference become indistinguishable from each other aside from the coordinates. If we choose any velocity much lower than the speed of light, then we notice that delta t prime is approximately the same as delta t. This is a domain of Newtonian physics, and it is what all of us are familiar with. If we look at the other extreme, when the velocity approaches the speed of light, then we find that the delta t prime approaches infinity. This is because if the train car would move at the speed of light, then the guy p prime would measure that the time stood absolutely still inside the train car. However, reaching the speed of light is impossible unless you are completely massless, like light itself. For everything else that has mass, an infinitely strong force has to be applied in order to make it happen, because your mass would be infinite as well. We will take a deep look at these things in a later episode, however. Thanks for watching.